All right, let's get started for David's talk. So this is the last session of the day. We made it to the next to last day of TASI. There's no fourth session today, and then again, there's no fourth session tomorrow. We'll have 3 in the morning. And yeah, it's been a long school. It's been an enjoyable school. I guess I shouldn't make too many finishing remarks because we still have one more day, but we are getting to the point where you will go back to your homes and like have dreams about sitting in a room with 60 other TASI students. Because what happened? Where'd they go? Anyway, we are delighted to have the last lecture from David Simmons-Duffin. So go ahead, David.
Okay, thanks. Okay, so last time we ended with this interesting statement that when you renormalize a detector, you get J as a function of delta. So now what we're going to do today, what we're going to start with today is actually doing it, okay? So I'll try to show you in practice how this works in the example of the Wilson-Fisher theory. So we're going to look at the Regge trajectory that we've been talking about the whole time, this leading to us trajectory that I called E sub j. Based on our discussion last time, we know that when we renormalize detectors, the first thing that we should do is pick the detector spin, J sub L, which is the Lorentz spin of the operator where the detector is lying along future null infinity. And this J sub L is not corrected in perturbation theory because the Lorentz generators are exact in perturbation theory. So we're going to start with such a detector, and I'm going to call it D sub JL. And in the free theory, D sub JL is just the same thing as E sub J with this dictionary between J and JL. Okay, so this is a detector with spin J sub L. That spin is not going to be renormalized, and what we'll compute is its detector anomalous dimension, this thing, gamma sub L. To renormalize it, we need to look at some correlation function that it participates in. And the one we'll be looking at is a correlator in states created by acting with phi on the vacuum in momentum space. So the detector is translationally invariant. So that means that the total momentum in this correlator has to add up to 0. So there's going to be a momentum conserving delta function in front of this thing. And this kind of matrix element is sometimes called an event shape. The idea is that you have some state. Here it's the state created by acting with phi on the vacuum in momentum space. And you're computing the expectation value of the detector in that state. So at tree level, this event shape looks as follows. First of all, there's a momentum conserving delta function. And then there's a what I'll call a vertex factor, which depends on z and p. And this vertex factor is completely fixed by symmetries, although you can also just go and compute it directly from the definition of this operator, this Baire operator. So we wrote an expression for it in the first lecture in terms of creation and annihilation operators, and you can use that expression if you want. Last lecture, I wrote an expression for this in terms of a bilocal integral of 2 phis along a null array. You could use that expression if you want. Either way, you're going to get to the same correct answer, and that answer is that v sub j of z and p is the following: integral from 0 to infinity d beta to the minus jl minus 1, and then a delta function that fixes p to be in the z direction. Okay, so the interpretation of this is just that beta is kind of like the energy And this is giving you a delta function of p and weighting the energy in a particular way. Okay. And so this expression is fixed by is basically fixed by symmetry. We know the homogeneity in Z has to be J sub L, and that fixes the form of this integral over beta. And then this delta function here, setting p equal to this, well, you know this had to be present because d sub j is JL is built out of creation and annihilation operators that only have support along the Z direction. Okay, good. So this is the observable we're going to look at, and this is its tree level expectation value. And so now we want to study loop corrections to this thing. And one important comment is that when we study loop corrections, there are a few different possible sources of divergences. One possible type of divergence could be in the state that you define. If the state that you write down is not actually a good state in the theory and is made out of Baire operators, then it can have divergences, and you might need to renormalize the operators that you act in the vacuum with. However, in the MS bar renormalization scheme, in the usual way that it's organized, you impose that phi is a renormalized operator, so that correlators of phi are finite. So you should think of phi as being a renormalized operator, and therefore there should be no divergences associated with it. And in particular, phi acting on the vacuum creates a good true state in the Hilbert space of the theory. So that means that if there are divergences present in this, they have to be associated with the operator, d sub jl, and we have to remove them by renormalizing the detector. Any questions about that? Okay, so let's do it. So this kind of correlator, in this correlator, the ordering is important. This is an example of what's sometimes called an in-in correlator, or Schwinger-Keldysh. The Feynman rules for it are a little bit different from the conventional Feynman rules, and I'll try to explain where they come from. So first of all, there's a kind of diagram that you can draw for these, which is a diagram containing a time fold. So here's the time fold, and the idea is that the region below the time fold represents ket. The region above the time fold represents the bra. And the detector lives on the time fold at future null infinity. So this is the diagram, and the idea is that this stuff down here below the fold is computed by the usual Dyson series. So you have a time-ordered product of e to the minus I times the integral dt of h of t. And then this insertion, phi of p. Okay, and this is the kind of thing that you normally deal with in perturbation theory. But the thing above the time fold is the path integral above the time fold is computing the Hermitian conjugate of this thing. And the Hermitian conjugate of this thing, if you just take the Hermitian conjugate of this expression, it becomes an anti-time ordered product, t bar. And then this exponential here is complex conjugated, so you just get an I times integral dt h of t, and then this phi of minus q. And then the detector, djl, lives between them. So when we write down Feynman rules for this thing, we're going to have some Witt contractions that contract phis within this stuff. And those, all of that stuff is going to get the usual Feynman rules for time-ordered correlators. We're going to have some Witt contractions that contract phis within this stuff, and all of that is going to have the complex conjugated Feynman rules. And then there will be Witt contractions that contract a phi below the fold with a phi above the fold, or a phi in the detector. And in those, the propagator will be different. It will be a so-called Whiteman propagator. So let me write down the rules. So an interaction above the fold, or so I'll start with below the fold, gets the usual factor I times lambda, and then if we're doing dimensional regularization, mu twiddle to the epsilon. And then above the fold, we get the complex conjugate of this, minus I lambda mu twiddle to the epsilon. Similarly, for propagators, below the fold, then we have the usual time-ordered propagator, which in momentum space is minus I over p squared minus I 0. And I'm writing 0 here instead of epsilon because I don't want to get confused with the dimensional regularization epsilon. And then above the fold, we have the complex conjugate of this, which is the anti-time ordered propagator in momentum space, I over p squared plus I 0. And then maybe the most interesting case is that is propagators that go from below the fold to above the fold. So the idea is that for those propagators, those are Wick contractions between an operator here and an operator here. And those operators are in a particular ordering. The one below the fold is on the right, and the one above the fold is on the left. So you need to use the two-point function, the free theory two-point function, for operators in a particular ordering, not the time-ordered two-point function, but a fixed ordering. And that's what's called a Whiteman function. So if you study this two-point function for operators in a fixed ordering, then you get the Whiteman propagator, which is just a delta function, an on-shell delta function, 2 pi delta of p squared, and then a theta function imposing that p be future directed. Okay? So, yeah, so that's what I'll say. Any questions about that? So all of this just comes from taking this expression, expanding it out, and using different kinds of two-point functions depending on where the Wick contractions are going between different kinds of operators. But there's also a path integral way of thinking about this, where the region below the fold is the path integral on one Lorentzian sheet, and the region above the fold is the path integral on a different Lorentzian sheet where the orientation is reversed. It's been complex conjugated. And then the fold is where you're gluing these two path integrals together at future null infinity. And the gluing is like inserting a complete set of states and summing over them. Okay, so in the path integral language, all this stuff about ordering of operators and whether they're acting on the vacuum or not, that translates into questions about the boundary conditions for the Green's function that you use in the Gaussian path integral. And the idea is that you have to impose certain boundary conditions on those Green's functions, and the different boundary conditions turn into these different kinds of propagators. These are all solutions to the Klein-Gordon equation with different boundary conditions. I actually really like that statement. I didn't when I learned about it in graduate school, just the idea that the different states and the different geometries of the path integral with all these time folds and things are all encoded in boundary conditions. I think that's a cool statement. Okay, so these are the rules, and now we're just going to apply these rules to this correlator. And the first non-trivial correction to the correlator actually comes at 2 loops. And it looks like this. So you have a phi particle coming in with momentum p, and then you use a phi-4 interaction to split this particle into 3. One of them goes through the detector, so one of them gets detected, and the others pass right through the time fold without getting detected. So the little cross here means the detector sits there. And then finally they join again at another interaction vertex. And then here's the out state with our p prime. And momentum conservation, of course, sets p equal to p prime. So I'll just call this p again. Okay, so this is the diagram, and this diagram is a really nice illustration of this notion of splitting that I talked about before. So it sounded that discussion sounded a little bit vague, but now we're going to make it really, really precise. And you can see what it actually means in like practical computations, what splitting means. So the particle's coming along, it splits into different pieces, and then the detector detects those pieces in a different way from how you might have thought, right? The detector isn't just seeing a single particle flying through, it's seeing part of the stuff that split apart due to an interaction. And at higher loop orders, you get more and more splittings, and the detector is going to detect one little piece of all this stuff that's flowing through the time fold. So hopefully that explains a little bit the words that I was talking about before. So we're just going to take this splitting picture and turn it into an equation. So the equation is just applying the Feynman rules to this picture. So I'll define F2 as the two-loop correction to this matrix element. Depends on Z and P. And so let's use the Feynman rules. So we have a minus I lambda mu tilde to the epsilon from the upper fold, the interaction on the upper fold, and an I lambda mu tilde to the epsilon from the interaction on the lower fold. There's a factor of 2, which is the symmetry factor from swapping these two lines. We don't permute the line that the detector sees. That gets treated differently. But there's a symmetry factor between these things. Okay, and now we need to label the momenta here. So we're going to call this momentum going this way, we're going to call it K. And the momentum going here that gets seen by the detector is Q. And then by momentum conservation, this is P minus K minus Q, this one. And it's we have to integrate over Q and K. So we get integrals over Q, integral over K. And then we have various propagators. We have time-ordered propagator down here, and an anti-time-ordered propagator up here. So let's write those down. I over p squared plus I0 minus I over p squared minus I0. And now we have the stuff associated with these three things. So this inside here, where for the particle that gets seen by the detector, that is just the tree-level matrix element up there, right? Because the tree-level diagram is stuck in the middle of this one. So that gives us this vertex factor, VJL of Z and Q. And then these two things, these are propagators that go from below the fold to above the fold, so they're Whiteman propagators, which are on-shell delta functions. And I should have defined this notation a little bit earlier. So what I mean by delta plus is this delta of p squared with the theta function that imposes that it be future directed. Okay, so this is the integral that we have to do. And this, fortunately, is actually the least scary two-loop integral you've ever encountered. And here's why. So the first thing to notice is that all three momenta propagating this way are constrained to be on shell. So these ones are constrained to be on shell by the Whiteman propagators, and this one is constrained to be on shell because the detector matrix element has a delta function imposing that P is null. This. And this is always true in these kinds of calculations. You always have on-shell things propagating through the time fold. And the interpretation is that you can insert a complete set of scattering states at the time fold. And basically what you're doing is you're just summing over the scattering states propagating through. And what that means is that because all these things are constrained to be on shell, these loop integrals turn into phase space integrals for those particles. So this really has, this directly becomes the square of an amplitude integrated over phase space. There's a very direct way to just translate between squares of amplitudes and correlators of this type. You had a question?
No, I think I
Okay.
understood.
Good. So what does this mean? It means this scary looking loop integral is actually a phase space integral. So how can we do it? Well, one thing we can do is this vertex has a delta function inside of it, delta of q minus beta z. And so we can use that to solve for q in terms of beta z. And then what these two delta functions do is they restrict k to the intersection of two light cones. So the first delta function says that k has to live on this future light cone. That's what this one says. And then this one says k has to live on the past light cone of p minus q. So we have to draw these two light cones, and they intersect at a sphere, which is an SD minus 2. So after solving all the delta functions, what you're left with is just the integral over a sphere, and it just gives the volume of the sphere. It's not a hard integral. So the final answer is lambda mu twiddle to the epsilon squared. There's a volume of the sphere, and then various factors. And there's some gamma functions, which come from doing the integral over beta, which is the last thing that you do. And then the interesting kinematic stuff that we care about, minus 2z dot p to the JL, minus p squared to the d minus 4 over 2 minus JL minus 2 theta of minus p squared. Let's see. Yeah, good. I should have probably said this at the beginning, but I'm working in mostly plus signature. So theta of minus p squared means inside the future null cone. Mostly plus signature, by the way, is the correct signature. OK, good. So we did this two-loop calculation, but it doesn't appear to be divergent. Good. So you were talking about these gamma functions. So yes, there are gamma functions, and indeed there are funny things happening with the gamma functions depending on JL. So you're right, and that actually will be very important later. But for now, let's take a value of JL that's generic, and then these gamma functions are totally fine. So, but there's no 1 over epsilon anywhere, apparently. This part of the analysis is very tricky. So doing the integral is easy. It's the easiest one-loop integral ever. But interpreting the answer is hard. So there's no free lunch. To interpret the answer, let me talk a little bit about divergences in distributions. So what is a distribution? It's something that you integrate against a function. For example, the Dirac delta function. It's not really a function, but it's a perfectly good distribution because we all know how to integrate it against a function. And usually you talk about distributions that can be integrated against some nice space of functions, what are sometimes called test functions. So a test function should be a function that's like as smooth and as quickly decaying as you want it to be. All right? So why do we care about distributions? Well, correlators in QFT in Lorentzian signature are distributions. That is their role in life. This is a stronger requirement than just thinking about them as functions. They actually have to make sense when you integrate against test functions. Maybe the most familiar case of this is that when you have an amplitude, it's a function of p, you should imagine smearing it against the wave function of the particles, right? And those wave functions you can think of as test functions, and those are the actual things, the actual physical observables. There's a sort of more fundamental reason that you should think about Lorentzian correlators as distributions. If you want to see a discussion of that, you can have a look at my Tazi notes from 2019, where I talk about this in a lot of detail. I unfortunately don't have time to go into it now. But the summary is that you have to think about these things as distributions. And when you do, you have to be a little bit careful. So let's take an example which is the following object. Theta of x, so x is just some variable, over x to the 1 minus epsilon. So this is a distribution that depends on a parameter epsilon. And what does it look like? It just looks like it's a theta function restricting that x be positive, and if epsilon is, and then it does this. Okay, and we can try to integrate test functions against this. And the claim is that this distribution actually has a pole in epsilon. So how do we see the pole? Well, let's imagine integrating this. So we're going to integrate x from 0 to some value L against a test function, f of x. And to see this divergence, it suffices to look very close to the origin, x equals 0. You can see something funny is happening there. And because this test function is as nice as it can possibly be, we can Taylor expand it around that point. Okay, so let's replace f of x with its Taylor expansion. So we get f of 0 plus x f prime of 0 plus dot, dot, dot. And we're allowed to do this expansion to analyze the singularity that we're looking for. Yeah, I'll just say that. And so now we can do the integral term by term. And indeed, you find that from the first term, there's a 1 over epsilon. So what is this integral? It's 1 over epsilon f of 0 plus dot, dot, dot. Okay? So this is an object such that its integral against any test function has a 1 over epsilon in it. And a nice way to summarize this is to think about the distribution as a good object on its own and say that it has a Laurent expansion in epsilon where the leading term is a delta function or a delta distribution. It's a little funny because when you look at this thing, you're tempted to think of it as a function, and as a function, it doesn't look like there's anything crazy happening at epsilon equals 0, but as a distribution, it has a Laurent expansion with a pole. Any questions about that? Yeah.
What is theta doing?
So the theta function is just just restricting to the positive axis, so I don't have to, because I'm taking a power of x, so I don't want to worry about negative x. Yeah. The question is, aren't test functions usually not analytic because they have compact support? I mean, they still have Taylor expansions, convergent Taylor expansions in some finite neighborhood. You know what? That actually is not even necessary. So the thing that's necessary for this argument is just that yeah, I realize that what I said might not be correct, but what you can do is the following. So if you're integrating theta of x over x to the 1 minus epsilon against f of x, you rewrite this as an integral of theta of x over x to the 1 minus epsilon of f of 0 plus integral theta of x over x to the 1 minus epsilon of f of x minus f of 0. And similarly, if this singularity were even stronger, you could subtract off more terms. And the point is that it doesn't really matter whether whether the Taylor expansion has a finite radius of convergence. The only important thing is that this is sufficiently suppressed near x equals 0 that this integral is finite. It has no pole. And then you can get the pole from this term. And actually, this is in practice, if you want to integrate a test function against a real distribution like this is actually how you do it. You split it into 2 pieces. This splitting is exact. Then this integral can be done analytically, and you can do this one numerically if you like, or analytically or whatever. Other questions? OK. So good. So this is a QFT correlator, and we have to think about it as a distribution. And you're going to have to trust me on this because we don't have time to go through the calculation in detail. But when you do an analogous analysis like this, you find that this actually does have a pole in epsilon when interpreted as a distribution. The idea of the analysis is the same as what we did before. You take this and you imagine integrating it against a smooth function. The interesting thing that happens is that this has some kind of non-analyticity. Well, really, this together with the theta function has some non-analyticity near the light cone. And this term has some non-analyticity when p becomes parallel to z. So you have to be careful near those locations. You look at your test functions near the locations, you do the integral carefully, and that's when the 1 over epsilon pops out. And it's the same way that a 1 over epsilon popped out here. It's just in more coordinates. So the claim is that minus 2z dot p to the JL times minus p squared to the d minus 4 over 2 minus JL minus 2 theta of minus p squared has a pole in epsilon that looks like the following. Pi over 2 epsilon JL plus 1. Then here's the interesting part. It's proportional to the tree level vertex. So this should make sense sort of intuitively because the tree level vertex is a delta function that restricts p to be in the z direction. And I just argued that all the funniness is happening when p is on the light cone near the z direction, right? So the funniness happens there, and you get a delta function there, and it looks like this. So you can plug this in, and overall you find the divergence of this 2 loop factor is minus 1 over epsilon lambda squared over 2 times 4 pi to the 4th, 1 over JL times JL plus 1, VJL of ZP. And here's the important physics observation. This divergence is proportional to the tree level vertex. In other words, the operator is multiplicatively renormalized. This is the same thing that happened in the first lecture where we looked at the phi squared operator, the local operator, and we renormalized it. So you write out a correlator of this phi squared thing, and you find that the divergence is proportional to the tree level 3-point function that we looked at. And the same thing just happened here. We looked at a loop computation, and we found that the divergence is proportional to the tree computation. So that means that the operator can be renormalized by multiplying by a factor that cancels this 1 over epsilon. And that's what it means for something to be multiplicatively renormalized. And so now we can define the renormalized operator, DJL, renormalized, as some renormalization factor, Z, that depends on JL, inverse times the Baire operator, and the correct renormalization factor is as follows. It's just this 1 over epsilon that we found, and it has this interesting JL-dependent behavior. And this thing, this z sub phi, is 1 over 1 minus epsilon lambda squared 12 times 4 pi to the 4th. This comes from diagrams where you insert a counter term on one of the legs, like this diagram or the counter term below there. So you add those up, and it gives this extra factor. So that's what our renormalized detector looks like. And now you can compute the detector anomalous dimension. Minus gamma L of JL is beta lambda, the beta function, times the derivative of the wave function renormalization factor, or the log of the wave function renormalization factor with respect to the coupling. So this is lambda squared over 4 pi to the 4th, 1 over JL times JL plus 1 minus 1/6 plus order lambda cubed. And I want to pause to make a comment here. So far, we have not set the coupling to the Wilson-Fisher fixed point at all. So the whole calculation so far has actually made sense in a non-conformal theory. It seems to be the case that in perturbation theory, these detectors, at least in perturbation theory, these detectors make sense in a non-conformal theory. But the renormalization of the detectors in a non-conformal theory is going to give you something that is not related in a simple way to light transforms of local operators. It's just something new. So this is the anomalous dimension that you would use in a non-conformal theory, for example, if you were using the Kalin-Zemansky equation to run the renormalization scale to different places. But we can finally, if we like, set lambda equal to lambda star and put everything together to compute this curve, j as a function of delta. And you get that j of delta is delta minus 2 plus epsilon squared over 9 times 1 over delta minus 1, delta minus 2, minus 1/6, plus order epsilon cubed. And if you take this equation and you solve it for delta in terms of j and expand in epsilon, you get back exactly the anomalous dimension gamma of j that we talked about last time. So indeed, you get the same Reggie trajectory, but in different coordinates. Yes? Why is this the only diagram we need to consider?
Yeah.
Good. I mean, you have to do a diagram by diagram analysis to see which ones contribute, and this is the first one that's non-zero. So for example, one example is you can look at a sunrise diagram below the fold, and this vanishes. You can try to construct, let's see. You can try to construct one loop diagrams, and they all vanish also.
And how do you know that's the only way you can construct with phi? Just because here it can be written as 2 phi and equal over the null.
The question is, how do we know that that's the only way you can what?
Contract D with phi field. For example, can the detector detect the two particle coming to D?
Okay, the question is, can the detector detect two particles coming in and going out? So the spirit of what's happening here is we're starting with a bare detector, where that's a detector. A bare detector is just defined by like, well, we're just defining it like this. Anywhere it's in a Feynman diagram, it looks like this. That's the bare detector. Now, we did a calculation, and we found that the divergence was proportional to the same detector, and therefore it was multiplicatively renormalized. However, something more complicated could have happened. We could have found a divergence that was not proportional to the same detector, and what that means is it's mixing. So we would have had to cook up a more complicated bare detector that the divergence was proportional to, and look at divergences in both of those, and we'd have some kind of matrix of renormalization factors that mix them. And in fact, we're going to do that in just a second. And that can happen and will happen in perturbation theory. So it's definitely going to happen that as you go to higher orders in perturbation theory, different kinds of bare detectors will start mixing with each other. And there's no invariant notion of this being a 2 phi detector. I mean, with a bare detector, you can say this is a 2 phi detector, this is a 4 phi detector, and so on. But the renormalized detectors don't have that notion. They all mix. All the bare detectors mix with each other to give the renormalized ones. Thanks for the question. Other questions? Yes.
So should I think of the 1 over epsilon divergence as an IR divergence of the detector or UV divergence of the amplitude?
Okay, the question is the 1 over epsilon an IR divergence of the detector or a UV divergence of the amplitude? It's I think you should call it. You should think of it as an IRR or a collinear divergence because it's coming from a region of the integral where things are approaching this null line, or the momenta are approaching the null line. So, yeah. Other questions? Okay, so we're going to make things a little bit trickier. I'm going to address the question that was asked over here a few minutes ago about, wait a minute, but what about this junk? And indeed, the poles over here, there were poles over here, and we also end up with poles over here. So here we got some kind of Reggie trajectory that has poles in delta in it. The problem is that the analysis that we did isn't really capturing this recombination effect that I was talking about before. So this analysis is good for the part of the trajectory that's away from the singularity where the operator and its shadow cross. But it's not capturing what's happening at the singularity. So what I want to talk about now is how to capture that. And the idea is related to your question. We need to start with a bigger space of Baire detectors, namely the leading trajectory and its shadow. And we need to think about divergences in both of them and look for a 2x2 matrix of divergences. So that's what we're going to do. And you'll see things will get a little weird. Okay, so we actually need to do some careful setup for this computation. So let me start with some definitions. So first, the computation is much simpler if we change the normalization of the shadow transform so that it squares to 1. So I'm going to define S hat j as a thing Sj that I defined a couple lectures ago, or last lecture, times some gamma functions. Which ensure that it squares to 1. So now this has the nice property that Sj hat squared is 1. And another important property is that Sj hat acting on something with JL equals 2 minus d over 2, that's just the identity. Like as an operator, it's as an integral transform, it's the identity integral transform. So these are you can check these equations, and I encourage you to check them if you like. And this is just going to be useful. It will simplify the analysis a little bit. And so now let me define the shadow trajectory d twiddle JL as Sj hat applied to the original trajectory at 2 minus d minus JL. So maybe a picture would be helpful. So we have the original trajectory on the Jufrachi plot that looks like this. So dJL would be up here. And the shadow trajectory looks like this. And dJL twiddle is down here. So it's the thing on the shadow trajectory with the same Lorentz spin as this one. Okay? Why am I talking about that? Well, it's because Lorentz spin is exact. So if we're going to study some kind of mixing problem, it better be a mixing between two things with the same Lorentz spin. And the mixing is going to be between these two objects. But there's a subtlety, which is that Sj at this value of j, which, by the way, this value is right in the middle. So that's this location here. At that location, this Sj hat is actually the identity. It's like literally the identity transformation. And that means that d twiddle at this location, 2 minus d over 2, is just equal to d at 2 minus d over 2. And this is bad if we want to study mixing, because when you're studying mixing, you start with a basis for your vector space, and that basis had better be linearly independent. And what this is saying is that we might try to use DJL and DJL twiddle as a basis, but the basis degenerates at a particular point. So it's not a good basis to use, and instead we should use a modified basis. So I'm going to define yet another kind of D, which we'll call DJL prime, as follows. So it's mu to the 2 minus D minus 2JL times D twiddle minus D divided by J minus JL minus 2 minus D over 2. So this is kind of like blowing up the point where they become the same. And basically, we know that when JL takes this value, 2 minus D over 2, these two things become the same. And actually, this power of mu is constructed so that it also becomes 1. So the numerator has a 0, and we're dividing by that 0 in the denominator to get something non-zero. Okay? So now we have a good basis of things to use, which is DJL and DJL prime. Really having problems drawing my JLs. And I'll define this as boldface DJL, this two-component object. But something funny happened to do this. We needed these factors of mu, and the factors of mu are needed by dimensional analysis. It's because these two things, although they have the same Lorentz spin, they don't have the same mass dimension. So we need to stick in a factor of mu, and that means that this basis object, although it's everywhere linearly independent from DJL, transforms in an unusual way under dilatations. I will leave this as an exercise, an interesting exercise. So the exercise is show that this two-component thing transforms this two-component thing at this very special value of JL right in the middle transforms in a log multiplet. In the free theory. Under dilatations. Okay, so this is an interesting fact. There exist detectors that transform in funny log multiplets in the free theory. It won't actually be that important for us because when we turn on interactions, this log multiplet is going to split into two conventional dilatation eigenstates. What I mean by log multiplet, by the way, is that the dilatation operator acting on this thing has a non-trivial Jordan block structure. Okay, any questions? Okay. Good. So we finally have our basis, and now what we need to do is compute divergences in matrix elements of these things. And we actually did the computation that we need already, because this is the matrix element of DJL, and to get the matrix element of DJL twiddle, we just apply this shadow transform, which ends up multiplying that thing by some gamma functions. And then we can take this difference of them and divide by stuff. So we actually already did the loop integral. So all you need to do is take this result and plug it in to find the divergences. Now, let's see. The maybe main tricky point is that when you look for divergences now, you have to be attentive not just to poles in epsilon, but poles in JL. And this is a pretty weird thing that you might not be used to in perturbation theory. So how are we supposed to think about that? So first of all, let me write what you find. So in the matrix element of DJL, if you look more carefully at not just poles in epsilon, but poles in JL, then you see a few more different kinds of poles. So there's a 1 over epsilon pole. You also get 1 over mixed poles between epsilon and JL of various kinds. And this is proportional to the tree level matrix element. And there's another pole, which is maybe the new ingredient for this analysis, that's just in J. And that is proportional to this D prime thing at tree level. Okay, so when you're attentive to poles in epsilon and poles in J, you find more poles. All of this comes from just looking at this object and treating it carefully as a distribution. So how should we think about these poles? By the way, J star is minus 1 minus epsilon over 2. Okay, some value of J. So how should we think about these poles in J? Like, should we worry about them? So what is our goal? We're starting with some bare operators, and our goal is to construct finite observables in the interacting theory. If there's a pole in JL, it means we've failed to construct a finite observable at that value of JL. And we need to do something about it. It's not okay to just leave those poles in there. We need to get rid of them. We need to renormalize the operator to remove not just poles in epsilon, but poles in JL as well. And I mean, this is in the spirit of our goal, which is to do everything we can to define the finite observables, because that is how we access the space of things that actually can be measured in the interacting theory. And so we're being forced to do something strange, which is subtract poles in J, but we should do it. So, but a kind of nice thing happens when you take this perspective, which is you can see now if you're attentive to poles in J, and you take this point of view that you need to renormalize the operator to get rid of those poles, then you can see that DJL and its shadow actually mix with each other. And this is, it's a little bit mind-bending because it's an instance of this mixing between a light ray and what you might morally want to call a light cone thing, right? DJL twiddle, which is inside DJL prime, came from the shadow transform, which is some kind of smearing over the celestial sphere. And this thing, DJL, was just associated with a light ray. And the mixing between those two things is captured in this formula, which fortunately I didn't erase yet. And there's a region of momentum space where there's a divergence, and that divergence is no longer localized on the light ray, but it's actually localized on the whole light cone. Oops. So you take this formula, you take its shadow transform to get the same formula with d prime on the left-hand side. And then you multiply by a matrix to remove all the divergences in epsilon and JL. And that gives you a renormalized two-component object, where I guess this is now a fancy Z. And you can now go and compute the anomalous dimension of this thing as a 2x2 matrix. So you apply the same formula from before. You take the log of this 2x2 matrix, the derivative of that with respect to the coupling, you multiply by the beta function. And I won't write out the full formula for the anomalous dimension matrix for you. But one thing I will say is if you then set JL equal to 2 minus D over 2 and lambda equal to lambda star, then you recover the Reggie intercept of the Wilson-Fisher theory. So maybe you remember from last time, the Reggie intercept was where we had this deformed Chu-Fracci plot that looked like that. And the Reggie intercept is the value of J right there. The value of J in the middle of the plot, the highest value of J in the middle. Okay, so you get the Reggie intercept, but then the new thing that you get is an expression for the actual light ray operator with those quantum numbers, which is sometimes called the Pomeron. So you get to look at the Pomeron, and it looks like this. So it's a contraction of a two-component vector with our two-component vector of basis states. And it's that. And the nice thing about that is now you can do this analysis, and now you can reuse your operator. You can reuse the Pomeron operator, and you can ask about its matrix elements in other more complicated kinds of states. And you have a definition of it, so you don't have to worry about all the divergences appearing again in those other correlators. Questions? Yeah.
All of this is only a two-loop result for now.
Good, yes. The question was, all of this is only a two-loop result, and that's absolutely right. Yes, this is only at two loops, and this kind of operator-level analysis of divergences and recombinations of trajectories has not been done, to my knowledge, in very many cases. These kinds of renormalization calculations have been done in QCD for a very long time, not exactly in the same language. My guess is it wouldn't take too much work to put them into this language. The calculations have been done, the loop integrals have been done, but I haven't seen it clearly spelled out in this language, and it's possible that the people who work on that don't see the need, which is fine, it's their decision. But I think it would be nice to do. So one nice thing to do that I don't think has been done yet is in this famous recombination of the D-glap trajectory in n equals 4 superior Mills or any conformal gauge theory, or any gauge theory, really. It doesn't even have to be conformal. So we have this D-glap trajectory and this BFKL trajectory. So people have understood at the level of the Chu-Fracci plot what the recombination looks like here. And that's, I think, a very old result. But simply sort of lifting it to the level of operators, I don't think has been done. So that's a nice thing to do. There's also the question of just doing this at higher loops in the Wilson-Fisher theory or your favorite other theory. And I think these things are all worthwhile because we don't really know a lot about the objects that are going to appear. I mean, this relates to your question. What kind of detectors do we need to include in our basis? And I don't know the answer to that in general. It could be that there are more kinds of detectors that we just haven't guessed yet, even in the free theory. And one way to discover them would be to do this calculation. Pick your favorite detector, compute at some loop order, 7 loops or something, and then look at the divergences that appear and ask, okay, can I give an operator interpretation of each of these divergences? And in that way, you might discover objects, more bare detectors that you should have started with. So I think that there's potentially a lot to be learned from that. Other questions?
minutes.
15 minutes. Okay. Yeah.
Is there something special when delta is factor vanishes?
Oh, the question is, does something special happen when this factor vanishes? So when this factor vanishes, the interpretation is that the anomalous spin on the Chu-Fauci plot is 0, and that should probably be the stress tensor. That should probably correspond to the stress tensor. Yeah, and indeed, delta equals 4. So good question. Other questions? Okay, so this closes the perturbative section of these lectures. And maybe I'll just mention a few more sort of open questions about perturbation theory questions about these kinds of things. So there's the question of what kind of things objects do you discover at higher loops? Are there new detectors that appear there? I think the problem of mapping out the Chu-Fauci plot in perturbation theory, like really fully mapping it out, not just describing this one recombination and this one trajectory, but asking about what happens down here at negative j, that's a really interesting question. And things could get really complicated because down here you have horizontal trajectories, which I actually haven't had time to talk about much, but you have horizontal trajectories even in the free theory, and you have more 45-degree trajectories, and they're all coming in. Not only that, the number of Regge trajectories can actually be infinite in certain places, because if you look at like 3 phi operators and you try to sprinkle derivatives between 3 phis, there are lots of ways to do it. And you can't capture this with like a single family analytically continued in spin. You actually need multiple families. You actually need an infinite number of families. And this means that there are locations on the Chu-Fauci plot where you have an infinite number of trajectories, and you have accumulation points of trajectories in delta space, and you have accumulation points of accumulation points. These statements, one way to understand them is from the light cone bootstrap, but there are probably other ways to think about them. So there's all sorts of really crazy stuff that could potentially happen, and I don't really know what happens, and I think I'd like to know the answer about all of this. Okay, so I have a few more pages in my notes. I was going to talk about non-perturbative stuff, what we know non-perturbatively. And I think since I have about 10 minutes, I'm going to make, this is going to get pretty sketchy. But I just kind of want to say some words about what is known non-perturbatively. There is a kind of formal construction of light ray operators in a non-perturbative CFT as bilocal integrals. The nice thing about this formal construction is that it manifests analyticity in spin, and it manifests the OPE data of local operators. It takes both of those two things and sticks them into one object. The idea is if you start with a correlation function, then you can define something called a partial wave, which is an integral over 2 points against a kind of wave function, which happens to be a conformal 3-point function. So what I mean by this 0 subscript is that this is just like a conformally invariant tensor structure. There's a unique one, and I just mean that function. So you go look it up in a textbook, and that's the function that I mean here. It's not a physical correlator. And these are various fictitious operators with different quantum numbers. So these twiddled operators have dimension d minus delta 1 and d minus delta 2, the so-called shadow dimensions. And then this is just a fictitious operator with dimension delta and spin j. And you can take your correlator, this is a physical correlator, and integrate it against this thing, and you get something called a conformal partial wave, which depends on delta and j. It depends on x and z, which are the position and polarization vector of this thing. And then it depends on all the other junk that was in the correlator, all the other positions of other operators. And this object is sort of this object packages together all the local OPE data. It has this nice property that the conformal partial wave has poles corresponding to operators in the OPE of phi1 and phi2. So the residue of the pole is a 3-point coefficient, and the pole is at the position of the operator, and the thing it multiplies is the physical correlation function of this ith operator with all the other stuff. And the way this works is that in this correlator, there's a regime where x1 and x2 are going close to each other, and when you integrate that against the right wave function, it picks out poles for every operator in that region, every operator that appears when x1 and x2 get close. So this thing packages together all the local OPE data in a nice way. So this is summed over I, where the sum is over all the operators with spin j in the OPE of phi1 and phi2. Now, if you try to take this thing and analytically continue it in J, you can't do it. And there's like a silly technical reason you can't do it. It's that if you look at this 3-point function, it wouldn't. You can't analytically continue it in J. It would have branch cuts. And in particular, this 3-point function has a piece in it that looks like it's a function of x1, x2, x, and z. Raised to the j. That's the numerator of the 3-point function. And the problem is that this thing can have either sign, depending on what the positions of the points are. And so you can't raise it to a non-integer power. You would have branch cuts, and you wouldn't know how to make sense of the integral. So this thing is not analytic in J. But we don't expect the local operators to be analytic in J. Instead, it's their light transforms that should be analytic in J. So there's a trick, which is that you can Wick rotate this to Lorentzian signature and then just light transform it. So instead of studying this, you study the light transform of P. So this is still the integral of the 4-point or of the correlation function phi1, phi2 dot 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 against a kernel, but now the kernel is the light transform of the original kernel. It turns out this actually is analytic in J. Technically, what happens is that the numerator of this thing is v to the 1 minus delta. That's this funny thing that happens with the light transform. And then there's a theta function that imposes that v is positive. So that's just an exercise. You take this conformal 3-point function, you light transform it, and you get this. And j doesn't even appear here. J is in the denominator. So the j dependence is down here. And whatever it is, it doesn't particularly matter for this point. It's just analytic in J. So this is consistent with our physical expectations. You have this thing that packages the local operators, you light transform it, and you get something that's analytic in J. And so now we have something that packages together all the local operator data when J is an integer and is analytic in J. And so the idea of this non-perturbative construction of light ray operators is to just strip out the correlator and think about the integral, the bilocal integral by itself as an operator. So you define this funny O as the integral of phi1 of x, phi2, or x1, x2, times this thing. So by construction, this has the property that when j is an integer, it gives the light transform of local operators. At least it has poles in delta that encode those light transforms of local operators. And by construction, it's analytic in spin. So So this is like a package of light ray operators. They're packaged together into a function of delta. And so then you can ask sort of like how this package works. And maybe I should write a formula. So at integer spin, it looks like this. This is just the light transform of that equation. So this is true by construction. Now what about a non-integer spin? So that's a mystery. So we don't know what the analytic structure of this thing is in the delta plane when j is not an integer. When j is an integer, it's guaranteed to have this structure. But when j is not an integer, we don't know. It could have branch cuts in delta. It could have double poles or triple poles or, I don't know, essential singularities. We don't really know. Now, there's a simple hypothesis. The simplest sort of hypothesis is that, in general, even for non-integer j, it looks like some function of j divided by delta minus delta of j, where delta of j is the Regge trajectory, the ith Regge trajectory, times something that you might call Oji, where this is the light ray operator with spin j on the ith Regge trajectory. This is the simplest hypothesis. Another way of phrasing it is just that it's the claim that this thing has simple poles in delta, even at non-integer j. But again, we don't really know. And these investigations of perturbation theory are actually really important, at least for me right now, in terms of like trying to grapple with this question. Because I don't know of non-perturbative techniques for figuring out the analytic structure of this thing. So I think looking at examples is really important. And so far, the examples from perturbation theory seem to support this hypothesis, which it was actually a surprise to me. But probably there aren't enough examples yet for me to like be really confident about it. Certainly, the examples we studied support this hypothesis, right? We had this perfectly nice Regge trajectory that made sense at continuous j. We were able to renormalize it, and everything was beautiful. One of the things that worries me a little bit is what happens if you start to think about places where there are infinite numbers of Regge trajectories, accumulation points of Regge trajectories, and they all start mixing with each other. Could be pretty scary, and I don't know what happens there. Now, and let me just say this. So let's suppose that the analytic structure were not this. What would it mean? And I don't know the general answer, but let me give an example. So what if this thing had a double pole in delta? What would that mean? Well, a double pole would actually just mean that there is a light ray operator, but it transforms in a log multiplet. We actually saw this example already. In the free theory, there's a double pole in this thing where the trajectory and its shadow cross. At the crossing point. And we found the log multiplet. It's this at JL is 2 minus d. So that's a thing that can happen. And actually, it does happen in the free theory. Maybe more stuff can happen. I don't know. I think studying examples is a great way to find out. I think that's the end. So I had a couple more things in the notes that you can look at. One comment was about the Lorentzian inversion formula. So if you study matrix elements of this object, you are led to the Lorentzian inversion formula, which is a beautiful formula that analytically continues the data of the CFT in spin. It's basically like, yeah, it's a beautiful formula. It's really nice because it's very compact and it's easy to study and it has lots and lots of interesting implications and it's been used in a lot of interesting computations. And I need to mention it because it was sort of the starting point for me on this kind of light ray journey. And so it was and is very important and dear to my heart. So thank you, Simone, if you're watching. And the other section is about the light ray OPE. So you can have a look at those if you want, and I'll stop here. Thanks. Yeah.
Do you have any idea what a branch cut would mean? Considering that's overextended.
So the question is, what would a branch cut mean? And I think that a branch cut, the idea would be that you should take the discontinuity across the branch cut, and then that's just going to be a light ray operator. I think any singularity that you can kind of, where you can like drill down on the singularity will correspond to some kind of light ray operator. The conformal transformation properties of that light ray operator will depend on the structure of the singularity. The case where I might worry is if there's like some kind of essential singularity. I don't know what to do then. John.
You said the phrase that OJI is the light ray operator on the ridge trajectories with spin J. Is it clear that there should be one? Like, is there a reason the trajectories are monotonic?
Okay, the question is there a reason that we should be able to enumerate the trajectories with a fixed spin? Is that the question? With an index I?
Well, so I thought I is like the trajectory of the.
Yeah, let me draw. I'll draw a picture. You can continue your question. So the idea is that like we have these trajectories. There's dragons down here, and the idea is we're fixing J, and then we're moving along this direction, and then we're looking at these things.
Right. So your picture, I mean, sort of assumes that each of them is monotonic, and they don't like none of them goes away, none of them crosses.
Okay, yeah, good. The picture is assuming something nice about this. So whatever these are, at every integer j, they'd better be consistent with local operators. So they have to satisfy the unitarity bound, which means that they're all to the right of a 45-degree line. Now, so that means it's very nice at every integer j. Away from integer j, other things could happen, and I don't know exactly what could happen. I know that in perturbative examples that people have studied, generally the trajectories just continue nicely through the local operators and they don't do anything crazy. So it's not like you don't have stuff where it's going down and then it shoots off to infinity and then it comes back this way and then it goes back to a local operator. I haven't seen that in any examples, but I don't know how to rule it out.
Could I ask a question?
What's that?
Could I ask a question?
I think there was another question there first, maybe?
Okay, yeah.
I just wanted to, how does the structure of light ray operators help with the bootstrap? Or do you want to try to bootstrap light ray operators?
Okay, the question is, can you bootstrap light ray operators? And so I think it sort of, I guess it depends on your definition of bootstrap. I think if you apply the strictest definition, which is that we want to run the numerical bootstrap and we want to get beautiful bounds and islands and stuff like that, I think at this point, like, not enough is known about these things. It is tantalizing, at least to me, that there's some kind of rigid structure here. Like, I like the fact that different local operators, which otherwise would look distinct, are connected to each other by some kind of analytic thing. And these connections between the spin zero operators and the higher spin operators that we talked about last lecture are really tantalizing. It suggests there's some rigidity to it, but I don't know how to use that or the extent to which it's useful. But maybe in a glorious future, you could imagine that we've learned enough about the Jufraci plot and its analyticity structure, and we have constraints on it to the point where you could try to bootstrap this Riemann surface. That would be great. You had a question, Oliver?
Well, yeah, I was just going to ask, I think I'm getting lost in the details a little, and I was wondering if we could just sort of circle back to the big picture. Like when my parents asked me, like, what is that nice David Simmons-Duffin working on these days? Like, well, there's these light ray operators, think of them as detectors in some way, but like, What's your big picture view of sort of where you're trying to go with it?
Yeah, that's a great question. So
What is it teaching me new? I feel like there's new directions in quantum field theory in here, but I'm trying to understand better and taking old directions and bringing them in a new way. And I'm sort of
yeah,
trying to understand how
yeah,
to
I think
say that.
there's a mishmash of different things in here. I mean, one thing is that I think that some of this language and techniques could be useful in perturbative computations for colliders. I think there are useful organizational principles here. The idea of thinking about operators, thinking about detectors as being things that make sense, could be practically useful. I guess I might hope that we could make some non-perturbative sense of the space of detectors in the same way that we can make non-perturbative sense of the space of local operators. And at least for me, it's hard to overstate the impact of the non-perturbative definition of CFT data. I mean, it's what leads to the conformal bootstrap. What leads to our notion that ADS CFT gives a good definition of quantum gravity because we're confident that CFTs are, make sense and are consistent objects. Okay, so maybe light ray operators aren't